Okay guys, so we're jumping back in. We're finding the area between curves, and as a reminder, we have 3 steps. We're going to sketch our curves, we're going to find points of intersections, and in this problem it's not actually going to be intersections, we'll look at that in a second, but we're going to find our bounds, and then lastly we're going to integrate from one bound to the next, and of the upper curve minus the lower curve. And it's important that we have upper minus lower, because otherwise our answer is going to be negative. So let's move on to this. So we've got number 3 here. Should probably a little bit, we'll try some like orange and green and stuff, see what happens. So number 3 says find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x equals 0, and x equals 1. So let's actually start by just looking at these. These 2 things are vertical lines. Trying to figure out what color I want to use. I'll start with purple for now. So these 2 things are vertical lines, and these are going to be 2 of our bounds. Okay, well, let's see if we can sketch this now. I'm going to mix it up. We'll use some green. So here's my graph. So again, this is step 1. Okay, before we had a negative x squared, now we have a positive. Ooh, that color's not showing up very well, is it? We've got y equals x squared plus 2. So I have a parabola that's facing upwards, and it's shifted up 2. So I'm going to go 1, 2. That's going to be the vertex of my parabola. When I go over 1, I'm going to go up 1. When I go backwards 1, I'm going to go up 1. And then if I were to go over a second one, I'd actually go up 4 from here. So 1, 2, 3, it's just kind of going to be right up there. Same thing, if I go backwards 2, I'm going to go up to that point too. So here's my parabola. So that's y equals, I'll call this f of x for now. Okay, now let's do y equals negative x. I'll use orange for this. I hope this color shows up a little better than that one did. Okay, y equals negative x, so a slope of negative 1. I think that's showing up a lot better. Okay, now let's put in my vertical line. So from 0 to 1. So what I have is this vertical line. It would really go up and down, but I'm just going to do it for the section that I need. I'm going to go from here until 1. So they want the area between the graphs and the vertical line. So you can kind of see that this boxy area here is the area that I want. So step 2 is to find my bounds. Luckily for this problem, this step's really easy. So if I want to find my bounds, my bounds are just going to be the x values that I'm integrating between. So I'm going to start at 0, and I'm going to go to x equals 1. So now I can jump into integrating. I want to find the area between f of x, and earlier I said I was going to label these, so I'm going to call g of x this second one. So I want the bounds from 0, I'm going from 0 until 1, of the upper curve. Well, f of x is my upper curve for this section that I care about, and it looks like it would be all the time, which is x squared plus 2. So x squared plus 2. Notice how I'm using my brackets and parentheses. I'm going to be subtracting 2 functions, but I need that dx to apply to everything. So I've got my bracket in my front. I've got f of x minus g of x, which is minus x. So I can really just write that as a plus x dx. And we've got space this time, so we'll do this by hand. So here we go. The antiderivative of x squared will be 1/3 x cubed. The antiderivative of 2 with respect to x will be 2x. And then for x, we'll have 1/2 x squared. And we're going to be evaluating this from 0 to 1. So if I plug in 1, I'll end up with 1/3 plus 2 plus 1/2 minus, if I plug in 0, those are all going to be zeros, which is really good. Now remember, if this is the AP exam free response, you're going to stop here and box this answer because you're done. But it can be nice to kind of know what the actual value of this is. So I'm going to keep going real fast. If I get a common denominator, I could do 6. So that's going to be 2/6 plus 2 plus 3/6. 2 is the same thing as 12/6. So I have 2 plus 3, 5 plus 12, so 17/6. Now, I still would only box this answer in the AP exam. They either grade the last thing that you put or like whatever appears to be the last, which would be 17.6. But just in case you make an arithmetic error, you want to say, this is what I want you to grade. So that's going to be your final answer for number 3. So let's move on to number 4. We're actually going to need a calculator for this problem. It says find the area for the region, of the region between the graphs f of x equals 3x cubed minus x squared minus 10x, and g of x equals negative x squared plus 2x. Let me grab my calculator. When you have a calculator, the first thing you're probably just going to want to do is graph these and see what they look like. So I'm going to go into y equals. This is an example of when if you've got one of the color calculators, it's really helpful to be able to see the difference between the two graphs and knowing which one's which. We're just going to have to use shape. I'm going to have to use the shape of the curves and what I know about cubics versus quadratics. So I'm just typing in my function. You should be doing this at the same time. I know I'm doing this for you, but you really just want to practice doing this by hand. Because on the AP exam, I will not be there to type things in for you. Hopefully my Windows is like a standard Zoom. If it wasn't, remember you can just go to Zoom 6. And I'm going to graph my curves. And this actually gives me a pretty good view. So a couple things that I know, f of x has to be this curve here that's coming up because it's cubic. You'll notice it had those two turns. And this has to be my g of x, my x squared. And you'll notice it says find the area of the region between the graphs. And you can see that they actually have 3 intersection points. 1, 2, 3. We don't find the area over here because there is no intersection point and it would just be infinity. They're specifically asking for the area between the curves here and between the curves here. And one of the things that you'll notice is that which graph is on top is switching. So we're actually going to have to write this as 2 integral expressions. One from this first bound to this bound, and then one from here until here. So let's actually just start by sketching this. I'm not going to be overly specific in my graph, but let me just start by sketching. So here's my function. I think this purple shows up pretty nicely, so I'll keep sticking with this. So f of x is a cubic. If I plug in 0, I get out 0. So I know it's going to go through here, and it looks roughly like it kind of just does this. So I'm just going to start by drawing it like that, and this is going to be f of x. So again, f of x is in this color. I like that orange, so I'm going to use the orange. So g of x is going to be this color. And it looks like that also goes through 0, 0. I'm going to have to be a little dramatic with my shape here just to make this work nicely, but it's a quadratic, so it's kind of coming in like this, and then it ends up crossing through here. So my shape isn't great, but that'll work for now. And this is g of x. So what I need to find is the area in here, but you'll notice for this section, again, f of x is on top, g of x is on the bottom. And then I need to find the area in here, and you'll notice for this section, g of x is on the top and f of x is on the bottom. So I need to find 3 bounds now. I need to find this first intersection, the second, and this one here. So I'm just going to make it clear by saying I need to find this, I need to find this, and I need to find this. Well, since this is a calculator problem, I'm going to let the calculator do the work for me. Now, there's a couple ways we could do this. We can actually like solve these by setting them equal and solving, which is something we can do, but I'm just going to use my calculator. So I'm going to do second calc intersect, which you guys can see. And I'm scrolling over to this first intersection point. But I already lost it. Well, that's convenient. X equals -2. I'll do it again. And I believe it's going to be at 0 because we talked about how they both go through the origin. Oopsies. 0, and then my last one over here, and 2. How nice. Now, if we actually had to solve these, I'm going to actually just do a little side thing here real fast. We could have that 3x cubed minus x squared minus 10x equals negative x squared plus 2x. And if I had to solve this, you'll actually notice conveniently that I have a minus x squared on both sides. Then I can consolidate on one side. I have a 3x cubed minus 12x equals 0. And if I factor out that 3 and an x, I'm actually left with this statement here. And you can actually find the zeros from that pretty easily. You're going to have a 0 of 0, and then you're going to get plus or minus 2 from that. So if you didn't have a calculator, you actually can find the bounds for this okay. But I'm just going to kind of make this as a little side note over here. Okay, so now we're finally on step 3, which is to find the area under the curve. And we said because of the fact that the one on top and bottom switches, we're going to have to write this as two different integral expressions. So let's do this first section first. I'm going to integrate from -2 until 0. You'll notice that I have f of x, for me it's purple, for you guys it looks like yellow, is on top, minus g of x dx. And separately, I'm going to then add the area from 0 to 2 of g of x minus f of x dx. Okay, and I'm going to type this right into my calculator because I did say this was a calculator problem. So let's go in and do that. I'm going to have math 9. I'm going to go from -2 until 0. F of x is 3. Actually, it would be easier to go into y equals. Oh, I already have them in y equals. How convenient. So when I go back to my home screen, I'm going to have from 0 to -2 of f of x, which I had in y1, minus y2, which is where I had g of x. It's going to give me my first piece. And then I'm also going to have to integrate, so math 9 from 0 to 2. But this time I had g of x on top, so I have to do y of 2 minus y1. And look at that, I had 12 and 12 of my two pieces. So my area for this first piece was 12. I thought I'd just subtract for a minute. The area for the second, so the complete area under the curve for both pieces is 24. If I had my bounds switched, I believe what would happen if you actually just went from -2 to 2 of the whole thing, I think you just get 0. We can actually test that theory real fast. So if I actually went, so like let's say I went just all the way from -2 until 2. I'm actually just curious what happens. Math 9 from -2 to 2. And let's just say we did f of x on top for the whole thing and g of x on the bottom. And just to be clear, this is not what you should be doing. I'm just curious what happens. So this is essentially 0, yeah. So what happens is if I don't switch the bounds correctly, this is going to get a positive 12, and then this is going to end up getting a negative 12 because your top and bottom are switched. So that would cause you to get the wrong answer. So the big thing you have to remember is when I have two curves that intersect multiple times, if the one that's on top and the bottom switches, you need to do those as separate integral expressions. So we've got one more to do together, and this one's important because it's a little bit different. It says find the area of the region bounded by the graphs, x equals 3 minus y squared and y equals x minus 1. So this is written the way we're used to seeing it, but this is actually going to be a sideways parabola. And you'll notice we gave you a hint that you're going to have to integrate with respect to y. So one of the things you guys are going to hear me say a little bit is when we have y's, I'll make a note of this now. Okay, so for y's, we're going to make a left-hand turn. And I'll get back to that in a minute, but I just wanted to write that down before I forgot. So let's start by drawing our graph because that's always step 1. So step 1 is to sketch our graph. So let me give myself a good coordinate plane. Now, when I look at this, I think this is going to be a sideways parabola. Because it's minus y squared, it's going to open towards like negative x values, and because it's plus 3, it's going to start at the origins, but it's going to shift back 3. So it's going to be here. Another way to do it, which is getting out with the left-hand turn, you can also take your paper, like if you're driving and you're going to make a left-hand turn. So if I were to spin my paper like I was turning to the left, I could also graph this like I'm used to doing, like a negative parabola. I had 3 minus y squared. So it would be upside down and shifted up 3, which would be graphed this way. So you can also do a left-hand turn and then shift it or graph it like you have on x's and y's where we're used to seeing them. So let me graph this again real fast. So I've got this point here. There's no stretch on that y squared term, so it's going to be a normal parabola shade of when I go over 1, I go 1, and I know to open up in this direction. When I go 2 from the vertex, I go 1, 2, 3, 4. Okay, so there's my parabola. And now I'm going to graph, so this here I graphed in purple. This one I'm going to graph in purple. So x minus 1, so I go down 1. And then I graph over 1, up 1, over 1, up 1. Okay, so I know that I need to find the area between these curves. And I think for most of you, it's going to be pretty clear that I'm going to be finding that area. Now, here's where things get a little tricky. When we integrate normally, we do the top curve minus the bottom curve. But you'll notice that the top and the bottom isn't always consistent. So until this point here, my top curve is g of x. My bottom curve is f of x. But then you'll notice on this side, f of x is the top and the bottom. So I do have the option of solving this equation for y and using the positive portion of the square root function and the negative portion as my top and my bottom. But here's the other thing I can do. Remember, when I see y's, so if I have y's in my equation like this, I'm going to make a left-hand turn. And when I make my left-hand turn, you'll notice now I have a clear top and a clear bottom again. This curve here, which is f of x, is now clearly the top, and this is clearly now the bottom. So it's actually going to be easier for me to integrate this time with respect to y instead of with respect to x. Now, because I'm going to be switching with respect to y, my bounds also have to be y values. So when I look at it this direction, you can see, okay, I have a bound here, like this is overlapping. Oh, this actually goes with this. And then I have a bound here. So we're going to integrate between these two things with upper minus lower. Now, I'm going to turn it around a little bit just to help me here. We can see from this that my bounds are at this point here, so -1 down 2. And this other intersection is here. This is going to be over 2, up 1. Oopsies. Okay, but if I'm going to integrate with respect to y, because I'm going to now use this as my top and this as the bottom, I'm going to use the y values. Therefore, we're going to go from y is -2 to y is 1. Now, if we're going to do everything with respect to y, that means my equations are going to need to be in the form of x equals. And you'll notice this thing here is already x equals 3 minus y squared because I need the y stuff in my integral. Well, I'm going to rewrite this one really fast, and I can isolate that x really easily, and I'll have y plus 1. So now when I go to write my integral expression, I can do this all in one piece, because remember, when I turn this sideways, this is clearly my top, this is clearly my bottom, okay? So I'm going to integrate from y is -2 to y is 1. And if you want to remind yourself, remember, these are y values. Okay. So I'm integrating from -2 to 1. My top curve is f of x. Remember when I had it sideways? So I'm using this expression here. Minus my lower function. Now we rewrote this so it was x equals, so I have y's in my expression. And I'm going to have dy. Now I'm integrating with respect to y. So whenever I want to turn my paper to make it so I have a clearer top and bottom, I'm now going to do everything with respect to y. Now this is something we certainly could solve by hand, but we can plug that into our calculator. So I'm going to do that real fast. You guys can see that there. So I'm going to go math 9. I'm going from -2 to 1. Now my calculator isn't going to let me do with y, so I am going to type this in with x's. X plus 1, close my parentheses, and then I would put a dx because I have x terms here. And that should give me my answer of 4.5. Okay. So guys, that's an overview of area between the curves. We will do practice of this a little bit in class next time. At some point, we'll have to do the homework that we're skipping tonight by doing the notes instead. But I hope you guys got through these okay. I'll take questions next time, and I hope we'll be able to clear up any questions that you have.